This is my Calculus 1 course. Today we're going to continue to learn how to find volumes of solids of revolution, but today we're going to use something called the cylindrical shell method. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. As usual, if you haven't memorized these formulas, go ahead and get a picture of those. In the previous classes, we learned how to use the disk method and the washer method to find the volume of solids of revolution, but today we're going to use, as we said, the cylindrical shells method. And this method says that if the area enclosed by the x-axis and these two vertical lines and some function f is rotated about the y-axis, then the volume of the resulting solid can be found with the following formula. And r is the radius of what we're going to call a cylindrical shell. So in order to explain why this formula works, we're going to use again what we call cylindrical shells. So here's an area that is enclosed by the x-axis and those two purple lines and the red curve, and we're going to rotate about the y-axis. So when we use the disk method and the washer method, we started by rotating about the x-axis. Well, now we're starting by rotating about the y-axis, and we'll talk about rotation about the x-axis using this method a little later. So we have a solid that is created when we rotate that area about the y-axis, and what we're going to do is find the volume of that solid by using shells. So look at this cylinder here. We've got a cylinder, and then we have cut the middle of the cylinder out. We've drawn a cylinder inside that cylinder, and if we subtract that inner cylinder from the bigger cylinder, we get what we call a shell. So this is the volume of the bigger cylinder. Its radius is R1, and this is the volume of the smaller cylinder. Its radius is R2, and we're subtracting, and that gives us the volume of the shell. Well, what we can do is we can strategically place these shells together, like you see here, and add up the volumes of those shells to find the volume of the solid created when we rotate this area around the y-axis. Now I'm only showing half of the shells. You see this part, that this half is missing because it's very difficult to draw this. If you look at textbooks, they don't have very many pictures of this because it's very difficult to draw. So this is not something that you're going to see a lot of people even attempt to draw. But this is my attempt to draw these shells. See how they're kind of put right next to each other, put in strategic locations right next to each other. And remember, when we rotate this area about the y-axis, we create a circular shape. That's why we're using circular shells to find the volume. Now, as the number of shells approaches infinity, and as the widths of the shells approach 0, because this is the width, you see that little that dimension there, that's the width of that shell, and this is the width of the next shell and the width of the next shell. As the number of shells approaches infinity, the widths of each shell, they're going to approach 0 because we're going to have an infinite number of shells. And so we're going to add up the volumes of the shells, and as the number of shells approaches infinity, the volume of all the shells is going to approach the actual volume of the solid of revolution. So let's look at this math here and explain why, or try to get a general idea of why this formula works and what it has to do with cylindrical shells. So again, we found the volume of the bigger cylinder and subtracted the volume of the smaller cylinder, and we have the volume of a shell. Now, if you factor h, see how we factored h? Both of these terms have h in them, so we can factor that h out. Now, normally we factor to the left, but you can factor to the right also. It doesn't really matter. Now, these expressions also have pi, so we can factor that out, and we're going to put it over here just because that's how it's normally shown in the formula. So we factored out pi and h, and we're left with this expression here. Now, that expression is the difference between two squares. Now, remember, there's three main types of factoring that you're going to see in the math curriculum. You're going to see the factorization of quadratic expressions that look like this. You're going to see factorization of the difference of two squares, which, well, just to give an example, it might look something like this. That's the difference of two squares. I didn't give actual values for A, B, and C here, but that's the quadratic. And then you have GCF factoring, when you have something like this. You can factor out a GCF. In this case, it's x cubed. Those are the three types of factoring that we have. And what we're going to do here is we're going to factor the difference of two squares. So just like this factorization would be x plus 2 times x minus 2, we're going to factor this expression so that we get r1 plus r2 times r1 minus r2. Now, we're going to do something kind of tricky. We're going to multiply by 2, and then we're going to divide by 2. If you multiply by 2 and then divide by 2, it's like you're not really doing anything. It's like walking 2 steps forward and then 2 steps back, right? You're not really changing anything. But the reason we do that is because this expression that you see here is considered the average radius. So we have our smaller radius, r2, and then we have our bigger radius, r1. If we find the average radius, that's the radius that starts from the center and it goes to the middle of the edge of the shell. You have the inner edge and then you have the outer edge. If you want to go right in the middle, that's r1 plus r2 divided by 2. And so we call that the average radius, and we can just take the subscript away and just call it r. We're going to do that eventually. Now, the height of the shell, obviously that's this distance here. The height of the shell is actually the y value of the function f of x. So if you have some point here, for example, your coordinates are x, y. Well, y is just f of x. That's the height of the shell. So let me show you a hypothetical shell in this solid of revolution that will help you to kind of see what's going on here, because it's very difficult to see what we're doing here. This would be a hypothetical shell. So it's circular. So you see that the height of that shell, that's given by f of x. Okay, so the height of all of the shells are going to be given to us by the y values of the points on the red graph. So h, the height, actually becomes f of x. Now, remember, delta means change. So when you have the difference between two values, you can call that delta. So we typically call the difference between r1 and r2 delta. Now remember, when we learned the basics of integral calculus, how to find the area under a curve, we added up the areas of rectangles, and the widths of the rectangles basically went to 0, or they didn't really go to 0, they approached 0. We used a limit to find the values the area. So we have our widths, so to speak, of the shells, but that width is kind of just going to disappear, you know. And we often think of that as being replaced with the ornament dx, even though dx is not really a thing. It's not really a value. It's just an ornament. So it doesn't really change to dx. It's just that when we use integral calculus, the fundamental theorem of calculus, remember, we don't even consider the widths of the rectangles. In the same way, we don't really consider the widths of the shells. And so we're just left with this expression in our integral. We can use the fundamental theorem of calculus and find the total volume with our knowledge of integral calculus. So we change this expression, or we put that expression in an integral, and that gives us the sum of an infinite number, the sum of the volumes of an infinite number of shells. So that is why the shell method works. Now, r, again, the average radius, which is the distance from here to here, remember, as the width, this is the width of the shell, right? As the width gets closer and closer to 0, you can see that we can just consider the average radius to be the actual radius of our hypothetical shells, and that's why average radius just becomes r. This is just general ideas indicating why this method works. If you wanted to do a rigorous proof, obviously you would need more than this, but we're just indicating why this method works. So that is the cylindrical shells method. Let's see how this works. Now this equation here tells us why this method is useful. Remember, and by the way, I want to remind you that usually we start by rotating about the x-axis. Well, with this method, we're going to start by rotating about the y-axis. Again, I want to remind you of that. So when you rotate about the y-axis, you want to solve your equations so that they're written in terms of y. So you want to solve for x. But if you notice, solving for x in this equation would be very, very difficult. It would not be easy at all. You'd come up with a fairly complicated expression. And so this is one example where the method of cylindrical shells is actually better than the disk method. So let's see how this works. We have this enclosed area. We're going to rotate about the y-axis, and we're going to use the method of cylindrical shells. So let me show you a hypothetical shell. Here's a hypothetical shell. And so we're going to calculate the volume of that shell. It's actually circular. And then we're going to calculate the volume of this shell. And then we're going to calculate the volume of this shell. And we're going to continue to find the volumes of more and more shells and add up the volumes, and that's going to give us the total volume. And again, the reason this works is because these are solids of revolution. We're rotating around, so that's why we can use these circular shells to help us calculate the volume. So I'm going to write the general formula that we're using. And now we're ready. So first of all, f of x, that's pretty easy. F of x is just going to be 4x minus x squared. That's the height of each shell. So f of x turned into that. So again, if I were to draw a hypothetical shell, this length here, that's f of x, because that's the length from the x-axis to the red graph. That's the height of each shell. Again, we can have shells in all kinds of different places. We can have a shell here, and we can have a shell here. The shells are going to be all over the place, but the height of each shell is always this, the distance from the x-axis to the red graph. And 2 pi, that's just always going to be 2 pi. And here's the part that kind of confuses students. What is r? Well, r is the radius of each shell. So let's say that we're talking about this shell here. The distance from here to here is f of x, again, as we said. But the radius, if this height is f of x, the radius of the shell is going to be x. Okay, because x is what you plug into the function to give you f of x, which is your height. And that's the part that kind of confuses students. In this case, r is just going to be x. X is the radius of each shell. Now you might wonder, well, if r is just x, then why don't we just make r x all the time? Well, in the next problem, you're going to find that r is actually not x. That only works when we're rotating about the y-axis. In the next problem, we're going to rotate about x equals 5. That's going to be different. So let me erase this and we'll calculate. All we have to do is calculate the value of the integral, and there's another thing that we need to look at, and that's the limits of integration. What are a and b going to be? This is another thing that is very confusing. So the limits of integration can be understood by asking what is the radius going to be for each shell. So we don't want to know what the range of the radii is going to be necessarily. That just helps us determine what the x values or the limits of integration are going to be. But we know that when we calculate our the volumes of our cylinders, the radius is the radii are going to range from 0 to 4. Okay. But x is the radius. So in this case, the limits of integration indicate the range of the radii of the cylinders. Now that's not always going to be the case, but in this problem it is. Now a lot of people say, wait a second, we need to integrate from -4 to 4. Why are we only integrating from 0 to 4? Well, that's because, first of all, we can't have a negative radius. And when you plug in some value for your radius, that helps you to calculate the volume of the entire cylinder, this side of the cylinder and this side of the cylinder. So you really only want x values that indicate the range of the radii. If you get confused, always remember that you just need to think about what the range of the radii of the shells is going to be, and the limits of integration can help you understand that. Again, sometimes these limits are going to be the actual range of the radii of the shells, but other times they're going to be numbers that you can plug in that will give you a range for the radii. Okay, so now I'm going to take out the GCF, which is 2 pi, and I'm going to distribute x. A lot of people don't like taking out the GCF out of the integral, but the reason that's beneficial is it makes it so where you don't have to rewrite that GCF over and over again, or you don't have to write it as much. Okay, so you do have to write 2 pi, but you don't have to. You're not going to have to write it as many times as you would if you distribute the 2 pi into these expressions. So now we're going to integrate. And we get the following expression, and we're going to plug in 4 into our antiderivative function. Then we're going to plug in 0 and so we're going to have 4 to the 4th power divided by 3, and 4 to the 4th power is 256, and then we have 64, and minus 0, all that stuff becomes 0, and if we put those expressions together, it looks like we're going to get 64 over 3. And if we multiply, we'll get 128 pi over 3. So there you go. So that's how that method works. Again, that's called the cylindrical shell method. We placed these shells in the solid of revolution, and we decreased the widths of each shell and increased the number of shells, and then calculated the volume, or the sum of the volumes of all the shells, and that gave us the volume of the solid of revolution. Now let's try another problem. This is the same exact enclosed area here, except we're rotating about the line x equals 5. So we're going to use the same formula. But r is going to be something different. We can rewrite f of x, that's just 4x minus x squared. That's the red graph there. And so we rotate about the line x equals 5, and we have this solid of revolution that, again, I'm not drawing the whole thing because it's very difficult to draw, but it's rotated all the way around. And finding the limits of integration and a value for r, that's going to be the hard part here. So we're looking for this r value, and we're looking for these limits of integration. So let's look at a hypothetical shell. So let's say we're considering this shell here. Now remember, this yellow shape, it's rotated around, so the shell is kind of following the shape. So let's find the radius of this shell. The radius is going to be this mint green length here. All right, but that radius is not x. X is actually this pink distance here. All right, that's x. And the mint green distance is going to be r. So we're looking for r. But, and by the way, the reason that this pink distance is x is because, remember, this length here, the height of the shell, that is f of x. So in order to make sure that we have the right height, you have to plug in the value of x that gives you f of x. That's this pink value. If you want to find the y value of this point here, remember we have x comma y, the y value of that point, that's f of x. But in order to find that y value, you have to plug in this pink x value. So x is the pink value, but we don't want the pink value. We want r, the radius. So what we have to do is we have to take the number 5, which takes us out to that orange line. 5, and then we subtract the pink x, and that gives us the mint green r. So again, this distance here is 5. We're going to subtract the pink x, and that'll give us that mint green r. So the mint green is going to be 5 minus x. All right, that's actually the radius. So let me write that in. So r is 5 minus x, and the height of each shell is 4x minus x squared. That's the hardest part for students. That can be really confusing. Students get really confused by this shell method because it's very different from the disk method. You have to think about this in kind of a different way. So now, here's another part that kind of confuses students. What's the limits of integration? The limits refer to x. And so we want to plug in values here that are going to give us a radius that is the right length, or it's going to give us the right range for the radii of the shells. So just looking at these hypothetical shells, this shell here has a radius of 2, right? Roughly a radius of 2. This distance here is 2. And if your shell goes all the way down to here, it'll eventually disappear. The smallest radius would be actually 1. And the biggest radius is when your shells go all the way out to here and they disappear again. The biggest radius would be 1, 2, 3, 4, 5. So the radii go from 1 to 5. So you want x values to be plugged in here that will take this radius from 1 to 5. So if you plug in 4, you get 1. If you plug in 0, you get 5. Okay. But we'd like to integrate in the other direction so we get a positive number. So instead of integrating from 4 to 0, I'm going to integrate from 0 to 4. So in this case, our limits of integration don't indicate the exact range of the radii of the shells. But when you plug the limits into this expression does give us the correct range of the radii of our shells. So you have to be very careful about what you're doing. So now we just have to integrate. I'm going to take the 2 pi out, and we're going to have to use FOIL here. So 5 times 4x is 20x. 5 times negative x squared is negative 5x squared. Negative x times 4x is negative 4x squared. And negative x times negative x squared is positive x cubed. Okay, so we can combine these two terms to get negative 9x squared. And now we're ready to integrate. So we have 10x squared minus 3x cubed plus 1/4 x to the 4th from 0 to 4. And let's see if we can find some more room. So we're going to plug in 4. And so we get 160 minus 192 plus 64. And all that's going to be 0. And so 160 minus 192 is negative 32 plus 64 is 32 times 2 pi is 64 pi. So the hardest part is figuring out what the limits of the integration are going to be and what the expression for the radii of the shells is going to be. So let's try a couple more of these before you try one on your own. So here we have a problem set. It says use the cylindrical shells method to find the volume of the solid produced by rotating the area enclosed by the graphs of each set of equations about the indicated line. It's highly recommended that you graph the equations to see the area rotated. So let's go ahead and do that. Let's graph. So here we have y equals x squared, and y equals x might look something like this. And this point here is going to be 1, 1. We can see that pretty clearly. You can set these expressions equal to each other if you want to confirm that. We also have the point 0, 0. That's a point of intersection. And so the area that we're considering here is this area here. When we rotate about the y-axis, we're going to have our area rotated like so. So we're looking for the volume of the solid that's produced when we rotate. So let's write our equation. And because we're rotating about the y-axis, the limits of integration are going to be indicated by the range of the radii of the shells. So if we draw a hypothetical shell, it might look like this. In this case, the height is going to be a little more difficult to calculate. The height of each shell is going to be this orange distance minus this green distance, and that will give us this this pink distance here. The orange distance minus the green distance will give us the pink distance. The pink distance is the height of each shell. Now the orange distance is just the y value of the purple graph, the purple line, right? And the green distance is the y value of the red graph, the purple, or excuse me, the red. So f of x is going to be x, the y value of the purple line, minus x squared, the y value of the red curve. So f of x is this entire expression here. Now r is just going to be this length here. If you want to find this height here, you have to plug in that corresponding x value that takes you out to here for both graphs, right? So that's just going to be x. Because we're rotating about the y-axis, r is just going to be x. Then we're going to rewrite 2 pi, and a and b, again, they just indicate or represent the range of the values for the radii of the shells. So this as the x value gets smaller and smaller to 0, you can see that the smallest shell is going to be down here. It's just going to get smaller and smaller and smaller, and the radius is going to approach 0. So the smallest radius is 0. The biggest radius is going to be the radius of this shell. The radius of that shell would be 1. So the limits of integration are going to go from 0 to 1. And so now all we have to do is calculate the value of this integral. I'm going to take 2 pi out. You don't have to take it out, but I prefer to just take it out. And I'm going to distribute the x. And so we have 1/3 x cubed minus 1/4 x to the 4th from 0 to 1. So 1/3 times 1 cubed minus 1/4 times 1 to the 4th power minus 1/3 times 0 cubed plus 1/4 times 0 to the 4th power. And all we have to do is calculate. So we have 1/3 minus 1/4 minus 0, and that's going to lead us to pi over 6. So there you go. Calculating the height of each shell was a little more challenging on this problem. So now we have the same exact problem, except we're going to be rotating the enclosed area not about the y-axis, but about the line x equals -1. So it's going to be a little different. So let's draw these graphs. We have the same parabola, and we have the same line. So we're considering this enclosed area, but now we're rotating about the line x equals -1. So that will be roughly here. Again, your graph doesn't have to be perfect. So when we rotate, our enclosed area is going to go over here. Now again, I know my graph is not perfect, but you have to picture area that's rotated all around like this, but we're only showing a sliver of the shape. So that gives us an idea of what we're trying to do here. So let's write our formula. It's good to rewrite the formula over and over again so we remember what it is. And let's draw a hypothetical shell. So here's a hypothetical shell. We need to find the height of the shell, and the height is going to be the same expression as we got before. It's just going to be x minus x squared. Again, we have to take this distance and then subtract this distance, and you get the height, this distance, the height of the shell. So that is f of x, the height of each shell. And calculating r is going to be more challenging. So let's draw a hypothetical shell. It really helps to draw hypothetical shells. So r, the radius of this shell, is going to be this distance. And maybe I'll draw it over here. That's the radius. That's the length that we want. We want that green length to be R. And maybe I'll just make it that same color so we don't get confused. We want this length here to be R. But X is this green distance. When you plug in an X value to get your height, the height of the shell, remember you want to plug in an X value that will give you this height and this height. When you subtract them, you want to get the height of the shell. When you plug in that X value, the X value corresponds to this length. But X is not the actual radius of the cylinder. The radius of the cylinder is this orange length here. So we need that orange length to be plugged in for R. So what you're going to do is you're going to take, let's see if we can find a different color. You're going to take this pink length, which is 1, because remember, this is x equals -1. So you're going to take that pink length, which is 1, and you're going to add it to x, and that is going to represent the radius of each cylindrical shell, 1 plus x. So I know that's kind of confusing, but again, that's why this can be very confusing for students doing these problems. So 1 plus x. And now we need to plug in limits of integration that are going to give us the proper range for the radii of the shells. So the smallest radius is going to correspond to this shell, which is actually not even present. It doesn't even appear, because when the height of the shell goes to 0, obviously it's going to disappear, but the smallest radius is going to be this length, which is 1. And the biggest radius is going to correspond to this shell up here, which again kind of disappears because as the side of the shell gets up into this corner, the height of the shell just goes to 0. But that radius would be 2, because this length is 1, and then we have 1 to get out to here, because this point here is, remember, 1, 1. So it looks like the radii of the shells should go from 1 to 2. But what limits of integration do we plug in for x to make that orange expression go from 1 to 2? Well, if we plug in 0 for x, that's going to give us an orange 1. The radius is going to be 1 of the shell. And if we plug in 1 for x, then the radius of the shell is going to be 2. Again, the shell is the orange part. Very confusing for students. So it's going to take some practice for you to get this down. So I'm going to take out the GCF, and I'm going to use foil. And so let's double check, make sure we got that right. Everything looks correct. So it looks like the math is not going to be too bad here, because the x squareds are going to cancel out. We're going to be left with x minus x cubed. And we're going to find the antiderivative. And plug in 1 to our antiderivative expression. So we have 1/2 minus 1/4 minus a bunch of zeros. And it looks like we're going to end up with pi over 2. Okay, so that is the cylindrical shell method. Go ahead and take a picture of these two pages and these two pages and these two problems, and get a picture of these two problems, and I want you to try your best on number 3. So let's first start by graphing so we can have an understanding of what exactly is happening here. We'll graph x cubed, y equals x cubed, which looks something like that. And then we'll graph y equals 0, which is that orange line, and then x equals 1. So it looks like the area that we're considering is this area here. Very important to understand what area we're rotating around. And we're going to rotate this about the y-axis. So we're going to have something that looks like this when we rotate around. Alright, so here's your formula. I'm going to give you the formula. I'm getting you set up here. And because we're rotating about the y-axis, r is just going to be x. So try number 3. So a hypothetical shell would be this blue thing here. That's a hypothetical shell. You might have another hypothetical shell here and another shell here. You're adding up the volumes of all those shells. So go ahead and try number 3. When you come back, we'll do it together. Okay, we're back. So you got that right. Excellent. Now, later on in the class, we're going to use the disk method to confirm some of these problems, to confirm our answers, because we can use the disk method on a number of these problems. You can use either method. Now, number 4 is going to be the exact same problem, except now you're rotating about the line x equals 4. So things get kind of confusing. The limits of integration are going to be different, and r, the expression that you come up with for r, is going to be different. It can be very confusing, so try your best. If you get stuck, that's okay. If you make a mistake, that's okay, but see what you can do for number 4. When you come back, we'll do it together. Okay, we're back. So I'm going to draw the graphs, and x equals 1 and y equals 0. So this is the area that we're talking about. We're going to rotate about the line x equals 4, which is somewhere over here. So I guess we're going to need to rotate all the way over here. So we're going to have something that looks like this. Okay, so a hypothetical shell might look something like this. So let's draw or write our formula. So go ahead and try number 4, and when you come back we'll do it together. Okay, we're back. Now we're left with 8 pi over 5. So we got that answer. Excellent. Okay, so you can get a picture of these two problems if you want. And I want you to try number 5. Now be aware, for this problem you have to be careful when you calculate the height of each shell. You're going to have to think about this expression and this expression here, or these two equations, when you calculate the height of each shell. So be careful. If you make a mistake, that's okay, but just try your best. In this case, we're just rotating about the y-axis, so the radius is just going to be x. But when you calculate the height, you have to be careful. The height of each shell. So try number 5. When you come back, we'll do it together. Okay, we're back. Multiply by 2 pi, and we end up with 5 pi. Okay, so we got that answer. Excellent. So in this problem, we rotated about the y-axis. Now we're going to rotate about the line x equals -1. So we have the same problem, just we're going to have to rotate about x equals -1. And we may have to use the differentiation formula number 12, if I remember correctly. I don't really remember if we'll need differentiation formula number 12, but that's the formula that tells you that the antiderivative of 1 over x dx is natural log x plus c. Again, I don't remember if we're going to need this one, but you might need that one, so just be aware of that. Okay, so try number 6, and when you come back, we'll do it together. Okay, we're back. Plus 7 pi. So we got that answer. Excellent. Okay. So now we're going to go on to dy integrals. So when we rotate about the x-axis, we're going to have to use dy integrals. And so we have the same formula, except instead of dx we have dy, and then instead of f of x we have f of y. And r is going to be written in terms of y instead of in terms of x. So for these problems, our shells are actually going to be orientated like this. So let's graph. So this equation is the same as y is equal to x squared. The only difference is x and y are switched. So whenever x and y are switched, you have an equation that is the inverse of the other equation, so to speak. So y equals x squared looks like this. If you want to switch the variables, then what you do to the graph is you reflect it across the y-axis, which wouldn't change this graph, and then you rotate it 90 degrees clockwise. So that would give you a graph that looks like this, something like that. So that is x is equal to y squared. Okay. X equals 0. That's this orange line here. And y equals 2. That's going to be somewhere up here. And so the area that we're we're considering is this area here. We're going to rotate about the x-axis. So that's going to look something like that. And this point here is going to be, I believe, 4, 2. And you can just plug in this y value here to find the x value. Okay, so let's use our formula. V is equal to the integral from a to b of 2 pi r times f of y dy. So now we're using f of y and dy as opposed to f of x and dx. So f of y is actually going to be the x, it's the height of each, shell. So here's a hypothetical shell. The height of that shell is going to be the x value of this red graph. But remember, we want to write it in terms of y. So f of y is actually going to be y squared. And because we're rotating about the x-axis, r is just going to be y in this case. And these green limits of integration, those are just going to be the possible y values. They're going to indicate the range of the radii of the shells. So the smallest radius is going to be 0, because when the shells get closer and closer inwards like so, the height is just going to go to 0. And the smallest radius of these tiny shells are going to be 0. And then when we get to the biggest shell, that's going to be here. That radius is going to be 2. So it looks like our limits of integration are going to be 0 to 2. So I'm going to pull 2 pi out. I just prefer to do it that way. And we have y cubed. So 1/4 y to the 4th power, 0 to 2. Plug in 2. Plug in 0. And, whoops, that should be a 1/4. And we're ready to calculate. So we have 2 pi times 4 minus 0, and that's going to be 8 pi. So there you go. So it's the same method, it's just that we're using shells that are, well, the base of the shell is on the y-axis rather than being on the x-axis, or it's parallel to the y-axis. Okay, now we're going to do a different problem. We're going to be rotating about y equals -2, but we're going to have a different equation now also. So if we were graphing y equals x cubed, it would look like this. But since we're graphing x equals y cubed, we're going to reflect across the y-axis, which will give us this graph, and then we're going to rotate 90 degrees clockwise, which will give us something that looks like this, the red graph. But we also have to subtract 1 from y cubed. Now we don't know what that means. We don't know how to understand what's happening to the graph, so we'll put the 1 on the other side. Then we have x plus 1 equals y cubed. So you can see that we're just adding 1 to x. So what that does, and by the way, I should draw that better. That didn't turn out right. Looks more like that. When we add 1 to x, we just move the graph 1 unit to the left. So these are all the things that you're expected to think about when graphing. And that should be red, probably. Okay, so x equals -1. That's going to be here. And y equals -2. It's going to be somewhere down here. And so the area that we're considering is this area here, and we're going to rotate about y equals -2. So that's going to give us the shape that looks something like this. So a hypothetical shell would be something like this, that blue shape there. Let's write our formula. You can see that this will be kind of confusing. It gets pretty confusing when you're changing back and forth between the disk method and the washer method and the shell method. The shell method, and you're changing from dx intervals to dy intervals, and things can get pretty confusing. Okay, so f of y, that's going to be this x value, which is y cubed minus 1. So the distance from this green distance from here to here, but we're going to have to subtract x equals -1. Actually, we're just going to subtract 1 because we want the height of each shell to be this green distance here. So we have this green distance minus this orange distance, the orange distance being 1. So that's 1. And then the green distance is going to be y cubed minus 1. So y cubed minus 1. And then we want to subtract 1. But actually, we're going to need to add 1 because the green expression gives us a negative number to begin with. So in order to take away, we have to add 1. So things can get kind of confusing. So it's going to be y cubed minus 1 plus 1. There's a lot of room for error in these problems. It's very easy to get confused. And r, the radius of each shell. Well, we need an expression for that. So the radius, this green distance here, that's going to be y. And this, let me get another color. This pink distance is going to be the radius. So again, that green distance is y. The pink distance is the radius that we're looking for. And the orange distance is -2. So it looks like we're going to have 2 plus y. and the reason it's going to be 2 plus y, there's a number of different ways to write it, but I'm going to write 2 plus y because y is a negative number. So the negative y is going to take away from the positive 2. So it's going to be 2 plus y. But again, there's different ways to write that. So that represents the radius. The limits of integration are the radii of our shells is going to range from looks like 0 to 2. So let's draw the hypothetical shells so we can see that. So the shell with the biggest radius is going to be down here when it actually disappears. The shell with the smallest radius, that's going to be somewhere like that where it has a radius of 0. So the radii are going to go from 0 to 2. So if we plug in 0, we get 2. If we plug in negative 2, we get 0. But I'm going to switch those limits of integration so we don't get a negative number. So I'm going to start with negative 2 and go to 0. So I'm going to pull out the 2 pi. And I'm going to simplify that expression. So we have y cubed. And then I'm going to distribute. And we get 2y cubed plus y to the 4th dy. And I'm going to find the antiderivatives of all this, so we get the following. I'm going to plug in 0. I'm going to plug in negative 2. Let's double check all this. Okay, so we just get a bunch of zeros over here. It looks like we get negative 8 there. And positive 32 over 5. So continuing to simplify, looks like we have negative 8 plus 6 2/5. And it looks like we're going to get a negative number. I forgot that because our graph is to the left of the left of the y-axis, when we integrate from negative 2 to 0, we'll actually get a negative number, but that's okay. We can just change it to positive because volume can't be a negative number, remember. So it looks like we're going to have negative 1 3/5. And that's the same thing as negative 8 over 5. And multiplying, we get negative 16 pi over 5. But we can just change to positive. So that'll be 16 pi over 5. Okay, so if you get a negative number, you can just change it to a positive. That just means that your limits of integration and the position of the graph are such that we got a negative volume. Okay, let's try one more of these. So we have x plus y equals 3. We can put the x on the other side. To see what this would look like, this is slope-intercept form of a line. Y equals mx plus b. B is 3. The slope is -1. So that's the y-intercept. Is 3, and the slope is -1, so a graph is going to look something like that. Again, it's not perfect, but something like that. And here we have the reciprocal relation. If we solve for x, we'll get the exact same thing if we rearrange and solve for x. So it just looks like our regular reciprocal graph. It doesn't really change when you flip or switch the x and y values. But we have a 2 up here, so that means the graph is going to look a little bit different. And we want to know what these intersection points are. I guess I'll make them green. I want to know those green intersection points. So in order to figure that out, we have to set these equations equal to each other. So if x equals 2 over y, and we can solve the other equation for x equals -y plus 3, and then set them equal to each other, we can figure out where the intersection points are. A lot of different ways we could do this, but I'll just set them equal to each other. The x values are going to be set equal to each other. And the fastest way to do this is multiply both sides of the equation by y. Then put everything on the left side of the equation. You get a quadratic equation, factor the equation, and we have y minus 1 times y minus 2. So when y equals 1, or when y equals 2, you're going to have the same x, or the same, you're going to get the intersection points. So here y is 1, here y is 2. So plug in 1 up here. Actually, sorry, that should be the y value, not the x value. So y is 2, plug in 2 for y, x is 1. Plug in 1 for y, x is 2. So this may seem complicated, but it's just basic stuff for finding intersection points. So that's how we find the intersection points. So all that work was to find the intersection. And then we're going to, looks like we're dealing with this area here. We're going to rotate about y equals -1. And y equals -1 is down here somewhere. So looks like our graph is going to look something like this. So a hypothetical hypothetical shell might look something like that. Actually, I didn't draw that very well. Look more like this. So let's draw our formula. Okay, so the height of each shell, let's draw a hypothetical shell again. That's a hypothetical shell. The height of each shell is going to be this distance here. You see that distance? So to find that, we take the y value of the purple graph and subtract the y value of the pink graph. Or excuse me, the x value of the purple graph and subtract the x value of the pink graph. So the x value of the purple graph is going to be negative y plus 3. And the y value of the pink graph, or excuse me, the x value of the pink graph is 2 over y, so we're going to subtract 2 over y. So minus 2 over y. Okay. And the radius of each shell is going to be this distance. And that distance is going to be this length, which is 1, plus y, which is going to be this distance here, that distance. So 1 plus y. And the limits of integration, well, the smallest, let's look at the radii. The smallest radius of the shells, that's going to be 3, it looks like. When the shells are down here, the smallest radius is going to be 3. This distance is 1, and this distance is 2. And actually, that's the biggest radius. The smallest radius is when the shells are going to be up here. And that radius is going to be 2, it looks like. So the radii should go from 2 to 3. So 2 to 3, so it looks like it's going to start at 1 and go to 2. So there's our expression. Again, it's difficult to see all that, difficult to set all that stuff up, but that's why these problems can be kind of challenging. Okay, let's take 2 pi out. And we're going to distribute 1 times negative y. And this is a situation where we actually are multiplying the sum of 2 terms with the sum of 3 terms. We don't do this very often in the math curriculum, but it does happen. So when we multiply, we're going to take the 1 and multiply it by all 3 of these terms, and then we're going to take the y and multiply it by all 3 of those terms, and then add 6 terms up. Again, that doesn't happen very often in the curriculum, but it does happen. So 1 times negative y is negative y, 1 times 3 is 3, and 1 times negative 2 over y is negative 2 over y. Now y times negative y is negative y squared. Y times 3 is 3y. And y times negative 2 over y is negative 2. So that is the expression that we're dealing with. So let's double check all this, make sure we got it right. Okay, now we're going to add like terms if we have any like terms. Negative y and 3y, that becomes 2y. And 3 minus 2 becomes 1. Then we have minus 2 over y, and I'm going to write that as 2 times 1 over y. And then minus y squared. Okay. So the antiderivative of that is y squared, the antiderivative of 1 is y. The antiderivative of 1 over y, remember that's natural log y. That's differentiation formula 12, I believe. And then we have 1/3 y cubed from 1 to 2. So let's go back over this, double check everything. Everything looks right. So plug in 2. And plug in 1. And then we just have to simplify. So you might be thinking, well, this is kind of tedious. You know, why do we have to do all this tedious work? Well, there's no avoiding it with calculus. Sometimes you just have to do some tedious problems. Looks like we're going to get 4 when we add all these terms together. And looks like we're going to get negative 8/3, and 1/3 is negative 7/3. And this is just going to be a 0. If you don't know exactly why that is, well, natural log 1, that means log base e of 1. To figure out what that equals, you set it equal to x, and then you translate it to an exponential equation, and you can see the only x value that would make that true is 0, so natural log 1 is 0. Whenever you have a 1 in a logarithm, it just makes it 0. Okay. So, looks like we're going to get 5/3 minus 2 times natural log 2. And finally we have 10 pi over 3 minus 4 pi natural log 2. So that is the final answer. Okay, so I want you to get a picture of these problems and these problems. And we're going to start out with an easy one. So I want you to graph this first. To graph, you can look at your library of relations. So if we had y is equal to square root x, it would look like this. But if you have x is equal to square root y, you're just switching the letters. So you rotate, or you reflect across the y-axis, which puts you over here, and then you rotate 90 degrees, which would give you this graph here. the orange graph. Another way to do that is to square both sides of this equation, and then you just get x squared is equal to y, so you know that that's just a parabola. But it's only one side of the parabola. It's only the side where x is positive, because here x can be plus or minus, but you don't see the plus and the minus. You only see the plus, so it's x cannot be negative numbers. So that's why we only draw half the parabola. Okay, and I'll make that red. This is x is equal to square root y, and x equals 0, that's this purple line, and then y equals 4. We'll put that up here. And so the area that we're considering looks like this area here, and we're going to rotate about the x-axis. So it looks like our shape is going to look something like this. Alright, so a hypothetical shell might look something like this, or it might look like this. So the height of each shell is just going to be this distance let's write our formula. Okay, so go ahead and try number 10, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Alright, go ahead and get a picture of this problem. And I want you to try number 11. Now, let's graph this expression together, because that may not seem very easy to graph. So let's solve for x. So we have negative y squared plus 3y. And how do we graph that? Well, that's a parabola that's going to look something like that, but we don't know exactly where it's positioned. There's a lot of different ways to graph this, but one way is to just factor out a y. And then we can see when y is 0 or y is 3, the parabola connects, or it hits the y-axis. It makes x 0. So 3 or 0. And we know it's opening this way because we have a negative there. But let's plug in, if we plug in y equals 1.5, we should be able to see where the vertex is. So 1.5 squared, make sure that's negative, so we get negative 2.25 plus 3 times 1.5, and we get 2 1/4. So x is going to be 2 1/4 out here somewhere. We also need the y-axis to enclose our area. So this is the area that we're considering. And we're going to rotate about the line y equals 3, which looks to be here. So it looks like our solid is going to look something like this. something like that. Again, it doesn't have to be perfectly drawn. So a hypothetical shell might look something like this, or like this, or like this. Again, we're adding up the volumes of an infinite number of shells. Okay, so let's draw our formula, or write our formula. And now it's time for you to try this problem, see what you can do. When you come back, we'll do it together. Okay, we're back. So we have 27 pi over 2. So if you got that right, excellent. Okay, so I want you to try number 12. Now, remember, y equals x cubed is, it's one of your parent relations. And to graph x equals y cubed, first graph y equals x cubed, and then reflect across the y-axis and rotate 90 degrees clockwise. So go ahead and try number 12, and be aware that there are two regions enclosed by these graphs, but we only care about the region from x equals -1 to x equals 0. So you may wonder why we have these vertical lines represented here. That's why. You want to make sure we're considering the right region. So try number 12. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. The reason we got a negative number here is because we integrated on the left side of the y-axis. So you can just change that to a positive volume, because remember, volume can't be negative. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and screenshot number 2. And number 3. And number 4. And number 5. And number 6. And number 7. And number 8. And number 9. But don't go before you get your homework. Remember, the homework is not optional. If you don't do the homework, you don't learn anything in this course. That's the way it works with every math class in the math curriculum. So take a screenshot here. This is screenshot number 1 of the homework. And screenshot number 2 of the homework. And screenshot number 3 of the homework. And number 4. And you can see that we have the answers to the homework at the right. So if you get the wrong answer, go back and fix what you did wrong. It's not enough just to attempt the homework. It must be done correctly. So get that homework done, and I'll look forward to seeing you in the next class.